Okay, so we ended class at this point where we had determined that the solution for an oscillating spring could either be a cosine omega t or a sine omega t. And we had reached this climax point and we had to stop class. So I'm glad that you can come back and see this video. So in this video, I want to go over making a general solution, unlike in class where we had talked about, we had talked about adding a phase angle and saying x equals a cosine omega t plus phi. What I want to show is that it may be easier to work with a combination of sine and cosine instead of that. So here goes. Okay, so I'm proposing that what I have boxed in is a solution for an oscillating spring that can work in any case. So let's start with a quantitative example. So in this example, let me switch over to yellow here. Let's let an oscillating system begin with x naught, pardon me, equal to 0.2 meters, which by the way would be 20 centimeters, and V naught is equal to -1. We'll say 1 meter per second. Okay, so let's determine what the specific solution would be for this case. Okay, so let's determine essentially C1 and C2, okay, for this case. And let's actually throw in some more things. Let's just throw in that omega. Oh, let's just go with, let's see, 2 pi over the period. So let's just say that it's 2 pi over 10. Let's go with, no, the period shouldn't be something like 10. It should be something like 0.5. So let's go with 4 pi for omega. Okay, so that will give us an oscillation rate. Turns out that won't be so important in determining this, all right? So we need to figure out what C1 and C2 are, okay? Now, we know that x is equal to C1 cosine omega t plus C2 sine omega t. All right, and we're told that at time 0, so x naught equals 0.2 means that when t equals 0, x is equal to 0.20. That's what x naught equals 0.2 means. So we can go ahead and fill that in. So we can say 0.2 is equal to C1 times the cosine of 0. It doesn't really matter what the omega value is, as I was saying, plus C2 times the sine of 0. Well, the sine of 0 is 0, so that goes away, and the cosine of 0 is 1. So what does this simplify down to? This simplifies down to 0.20 is equal to C1 times 1 plus 0. So C1 must be 0.2. So we've already determined what the constant C1 will be. And notice that, well, we'll come back to this later, that more generically, that is the initial position value. All right. Now, let's try to figure out what C2 would be. All right. We can't substitute in that the velocity is -1 until we have the velocity equation. So what we're going to do is take the derivative of this. So V is dx dt, which notationally we're often using x dot now. So if you have C1 cosine omega t, we know that the derivative C1 will remain. The derivative of a cosine, is, I'm going to erase that, is a negative sign, the derivative of a cosine. So I should be writing a sign there. There should be a negative out front. But then because of the chain rule, we're going to get an extra factor of omega right there. Okay, now we get to the second term. All right, so we have plus C2. The derivative of sine omega t would be cosine omega t, and then the chain rule will give us a factor of omega out there. So that's what our velocity equation should be, okay? But from the given information, we know that when time is 0, v is equal to -1. That's exactly what v naught equals -1 means. So we can substitute in that -1 is equal to negative omega times C1, okay, times the sine of 0, because omega t will be 0 when t is 0, plus omega C2 cosine of 0. Okay, now just like before, that means certain things will go away. This goes to 0. That simplifies down to a 1. So we can say negative 1.00 is equal to omega times C2. And we said for this example, omega is equal to, I think we said 4 pi. Let me just double check that that's what I said. Yes, omega equals 4 pi in this example. So 4 pi times C2. So C2 is negative 1 over 4 pi. Okay, we could give a decimal approximation of that. If we were doing a problem, we probably would. I don't have my calculator. Oh, actually, I do have my calculator right here. So let me just do that real quickly. 4 times pi. Okay, and then 1 divided by answer. Okay, so that is approximately negative 0.0, looks like 80. Okay, so that's what my C2 value is. So I can put all of this back together again and say, x would be equal to C1, which is, all right, 0.20 cosine of 4 pi, omega was 4 pi. So cosine of 4 pi t, putting parentheses around that might be helpful. It's not necessary, but probably helpful, minus 0.080, put parentheses around that, times I'll put parentheses here as well, times the sine of 4 pi t. So that will perfectly describe what happened in our initial conditions. Okay, so let me just review what we did real quickly. We basically have been given 2 data points, one for position, for the initial position, and one for the initial velocity. Okay, so what did we do? We have the position equation, and we take its derivative. So we then have a velocity equation. So we have a position equation, and we have a velocity equation. We substituted the position point in. You could, actually, there are a couple of orders. You could take the derivative right away, and then you could substitute in the data for position at time 0 into the position equation, and then you could substitute the data in for the velocity at time 0 into the velocity equation, and then that allows us to figure out what C1 and C2 are in this case. Okay, so that's what we can do. Now, we could be more generic about this. Okay. So let's look at the general case. Okay, so in general, x is equal to C1 cosine omega t. So omega could be anything, C1 could be anything, C2 could be any value. The derivative of that will be the velocity. So because of the chain rule, we know this is negative omega C1 cosine, whoops, erase that, that would be a sine. The derivative of cosine is a negative sine. And then we will get, by the chain rule, like in the last example. Okay. Now, generally speaking, we can say at t equals 0, x is equal to x naught, and we can also say v is equal to v naught. So let's first substitute in that x equals x naught. Okay, so if I take x, I can use the x equation and substitute x naught is equal to c1 times cosine, and when t is 0, this will be cosine of 0, plus c2 times the sine of 0. And as we've already talked about, the sine of 0 goes to 0, so that term goes away. And we can simply say that c1 has to be x naught. That will be true no matter what the x naught value is. All right. We can continue and look at the velocity equation. All right, so let me switch to, I'll switch to green for this, okay? We know that V is equal to V naught, all right? And that should be negative omega C1 at time 0, that's the sine of 0, so we're doing this all at time 0, plus omega C2 cosine of 0. And this time, we can see that this term will go away. That the sine of 0 is 0, cosine of 0 is 1. So what happens here? V naught equals omega C2. All right. So what's true? Okay. C2 needs to equal V naught divided by omega. Let me just make sure that I got this correct. So omega, yes, when we take the derivative, that is what happens. So C2 has to equal V naught over omega. So now we can write in a more general sense what has to be true. We can say, let me switch back to white here. We can say x is equal to C1. Well, C1 is x naught cosine omega t plus V naught over omega, that's C2, times the sine of omega t. So this would give us the general equation of motion. Now, one final quick note is if I wanted to get the solution for y, we know that y is equal to the stretch from equilibrium. So you have to add the equilibrium value on to how much it's stretched. So x is how far above or below equilibrium we would be. So in general, whoops, this is not an EQ here, that's y. Y will equal x plus YEQ. So we could say y is equal to x naught cosine omega t plus v naught over omega times the sine of omega t. Oh, plus YEQ. Okay. Now, one final little teaser. We know that the motion can be described by x equals x naught cosine omega t plus v naught over omega sine omega t. But we also know from class that x equals a cosine omega t plus phi. Okay, so both of these expressions must be equal to each other. All right, so we're not going to do this right now, but a must be some combination of x naught and v naught and omega. Okay, so to get that a value, we would have to figure out something about that, and we'll talk about that later. It's a little bit complicated, so I don't want to say that right now. And then we know that the phi shifts a cosine value. Okay, last year in pre-calculus we learned that, or 2 years ago in pre-calculus, that combinations of sines and cosines when added together if you were in the form of A cosine of theta plus B sine of theta, the addition of those will end up giving you a new constant. We'll call that C cosine of theta plus some sort of phase angle in here. Okay, and we'll talk later about how to get the phase angle just right based on what the x naught and v naught values are. Okay, so those things can be related one to another. But we'll say that for another video because that gets a little bit more complicated, and I suspect that your brains are quite full.